Okay, our new topic is to find the volume of solids with known cross sections, and this is also known as, sometimes you'll hear it referred to as volume by slicing. So it's either volume with known cross sections or volume by slicing. So our warm-up, as you can see, and I don't know what page this is in your packet, but you can find the page and take the notes in your packet. Our warm-up is to write the formulas for the finding the area of the following polygons. And the first polygon that we're asked to find the area of is a square. And since a square has all four sides that are congruent, the area of a square is side squared, and S representing side. The area of a triangle is 1/2 base times height. The area of a rectangle is base times height. The area of a semicircle is pi r squared over 2. And the one that you may not be quite as familiar with or might not remember unless you've taken the SAT recently, because it's one that pops up, but it is one that you're going to need to know. So if you don't know the area of an equilateral triangle, make sure that you set this to memory, because they do like to use this one on the AP test. And the area of an equilateral triangle is the square root of 3 over 4 multiplied by a side squared. Again, just commit that formula to memory, and you'll see in just a few moments why we're going to need those formulas. Now let's talk about where we've been, and then we'll talk about where we're going. We are going to find volume by slicing, as I indicated in the objective. What we've done so far, going back to what we've already done, we have found volume by revolving. Now I want you to keep in mind that when you revolve, that you're always going to make circles. And so every time we found the volume by revolving, and we just had a test on this, we either had a solid object or we had an object with a hole in it. And when we had a solid object, we know that the area of any circle, is pi r squared. So when we found the volume by revolving and when we were making circles, every single time we were using the formula pi r square, or if there was a hole in the object, we would have pi big R square minus pi little r square. But the big idea is when you are revolving, you always get circles, and every time you get circles, you collect all of that area, pi r square, and you get the volume of a solid. Okay? The new idea is that instead of revolving an object, we're going to be given an object that possesses volume, so it'll be the three-dimensional object, and we're basically going to slice it. So I'll probably start talking about these problems as a cake, and you'll see that in a few minutes, that we have a cake sitting on a plate. Now to find the volume by slicing, it's pretty easy. We're going to have a start point of A and a start point of B. There's no surprise there. And we're going to collect, just like we did before, we're going to collect area, but we're not going to collect the area of circles. We're going to collect the area of different shapes. So we'll collect the area of the cross section. So before, where everything was circles because revolving, this time we might have what I'll describe as a cake shaped as a square. So when we slice it, we'll get squares, we won't get circles. Or we might have a cake shaped in the form of a triangle, so that when we make slices, we get triangle slices instead of circle slices. So it's pretty much the same idea, except we're going to be dealing with other shapes than circles. Okay? So let's take a look at what these objects might look like. So this is also in your packet. In this first example, what we have is a circular base. Now I want you to notice the orientation of the x and the y axis. They've turned this thing so that the y-axis is running horizontally. It's just like taking a piece of graph paper and turning it. That's all that's happened. And what they're trying to do is they're trying to sit this object up so you can see what it looks like three-dimensionally. So when you think of this, I want you to think of this kind of like a cake. The plate of the cake, let me get my pencil here. The plate of the cake is the circle. So this is the base that the cake sits on. So in this case we have a circular base, but the cake itself is a series of squares that are getting bigger. And so I have a website that I'm going to show you in just a second to kind of give you a better idea of what do these solids actually look like. But think of it as we have this plate and someone has baked a cake, and the cake is a series of squares that are getting larger and larger and larger. So that when we slice this cake, if we were to come through and make slices, people would be getting a square, a square, a square, and as you go from front to back, you get small squares and larger squares and larger squares. It's just like when we talked about feeding the world with a ham. The first person gets a small circle or a big circle and a bigger circle, smaller circle, etc. Okay. In the second example, again, the x and y axis, and they oriented this so you can see what this object looks like three-dimensionally. In this case, our plate, or our base, is a triangle. So we're sitting a cake on a triangular shaped plate. And this time someone baked a cake and they made the cake into the form of a semicircle, and these semicircles are getting larger. So the first person that we slice, assuming we're slicing from front to back, gets a small semicircle, and as we move to the back, they're getting larger and larger semicircles. But again, I want you to keep in mind, we're going to collect the area of these infinite semicircles to accumulate. There's where integration comes in to get volume. And then the third example, we have a circular plate or a base. And that's important to understand what the shape of the base is. That's going to have an impact on what we do. And this time we have, again, a triangular shaped cake. Okay? Now I want to take you to a website just to show you some better graphics of what these things might look like. This is Volumes Gallery. So let's take a look. I have some in particular I want to look at. The first one I want to look at is the semicircular cross sections of a solid. Oops, I guess I can't write on that. Whose base is in the XY plane. So I'm looking right here. If you're wondering where I'm talking about. So in this case, the base is going to be the square root of x. And then we're going to fill it with semicircles. Now I'm going to click this, and what it's going to do is it's going to show you what the base would look like on the x and y axis, and then what would happen when you make it three-dimensionally and you put the slices in here, just so you get an idea of what these things look like. So here we go. Alright, so there's your base, the square root of x. Here's the x-axis and the y-axis. There's first slice, second slice. And really what we're doing is we're going to put an infinite number of slices in here, but this is just giving you an idea of what would this cake or what would this solid look like. Our plate, our base, was the square root of x, and then we made a cake out of semicircles, and this is what the cake would look like. So that's just to give you an idea of what that looks like. And it's going to keep doing that over and over again. Just a couple more, and you can go to this website if you can read the website link at the top. Let's look at this one right here. The square cross sections of a solid base. The base is an equilateral triangle. Remember I said how they like that. So the base is an equilateral triangle, and the cake is going to be in the shape of squares. So let's see what that looks like. All right, there's your equilateral triangle, the x and the y axis, and here we go. We're building our cake. It's made out of squares. And it's slicing lots and lots and lots and lots of squares. Okay, keep going, keep going, keep going. And so hopefully you get the idea of what that thing might look like. Now if you looked at it from the front side or from the X side, you would see a square. But from the side we're looking at, it looks triangular. All right, let's go back and do maybe one more. Okay, the next one that we're going to look at is another square cake, but this time the base is going to be a quarter of a circle, and then we'll do one more. All right, so there's your semicircular plate or base. Now we're building the cake. The cake is going to be made out of squares. So when we slice, everybody's going to get a square. So the main reason I wanted you to see this video is to, or this animation, is to see that we really are going to have an object that has volume, and we're going to slice it, but instead of getting, the only difference that's going on here is that instead of getting circles, we're going to get other geometric figures. Okay, so if you look at the next section of your packet, there is a complete description of how to find the volume by slicing. If the area of a cross section is known, then the volume of the solid is given by, well, we've already said this. We're going to have a starting point of A, a stopping point of B. We're going to have the area of the cross section. It might be a square, might be a triangle, might be a semicircle, or whatever. And then we're going to have dx or dy depending on what we're integrating with respect to. Now, this is very important right here. Rule. If the cross section, and they will tell you this in the problem, is perpendicular, this is the key word, perpendicular to x, we're in terms of x. Perpendicular to y, we're in terms of y. So make sure you highlight that in your notes to remember so that you know whether you're going to be in terms of x or in terms of y. All right, so you can read through this on your own, but I'm quickly going to read it with you. To find the volume of a solid with a known cross section, the first thing you're going to do is you're going to sketch the base of the solid. Now the base is like what I talked about as the plate. And then you're going to sketch or envision the solid. Now envisioning the solid, it depends on how good you are three-dimensionally. That's not the most critical thing. You're going to determine whether the integral should be in terms of x or y. You're going to determine the bounds. You're going to use geometry. You're going to set up your integral, and you're going to integrate. All right, you can refer back to this page if you get stuck. So let's look at an example and really see what's going on here. In this first example, in every problem, we have, as you can see, a sideways parabola. Now notice this is the x-axis and this is the y-axis. And they've drawn this one for you. We'll do one in a minute where we kind of draw it ourselves. We're supposed to find the volume of a solid that has r as its base, and r is the parabola, sideways parabola, if every cross-section in a plane perpendicular to the x-axis. So right away, I know that I'm going to be in terms of x because we're perpendicular to the x-axis. And this time, we're going to make a square cake. So the base, again, this is the base, the parabola, and the cake is going to be a square. Now you don't really have to draw that three-dimensional square. What you really need to be able to do is to identify the side of a square. That's really all we need to be able to do right there, is to figure out the length of a side of a square. Alright, so here's the process. Since I know that I'm making a cake in the shape of a square, the first thing I'm going to do is write down the formula for the area of a square. And the area of a square is side squared. Now we know that this problem is going to be in terms of x because we're perpendicular to the x-axis. So we're going to have dx. And since this is a square, we're going to have a side square. Our big job is to figure out what is the length of that side in terms of the base. Okay, again, the question is, what is the length of that side in terms of the base? In other words, how long is a side of that square? Now also notice that there is no pi in front of the integral because these are not circles and we're not revolving. All right, let's take a look. Here's my x-axis right here, and here's my y-axis. Now what I'm trying to figure out is the length of this side of this square, but I'm trying to find it in terms of the parabola. Well, obviously from the x-axis, from here to here, that distance is the square root of x. And if that distance is the square root of x, then since this is a square, that also has to be the square root of x. So remember, what I was looking for is how long is a side of that triangle? Well, a side of that square is 2 square root of x. So remember, now all we have to do is accumulate area of a lot of squares. So we're going to take our side, substitute it in here, and we get 2 square root of x. Because remember, the formula for the area of a square is a side squared. I found my side, and now I'm squaring it. From the figure, you can see, and I think they tell me that we're stopping at x equal to 9. We can see from the graph that we're starting at 0. We're stopping at 9 because they told us in the problem 0 to 9. And then cleaning that up just a little bit, I'm not going to integrate it all the way out. So we get 0 to 9 of 4x dx. And from there, that's not a really difficult problem to find the integration of. But what we're doing is we're accumulating or adding up the area of an infinite number of squares. And so we've used a formula for the area of a square. All right, let's take a look at number 2. In number 2, we have the exact same base. So again, we know that our plate, so to speak, is a sideways parabola. Now, I know that they gave us the function as x equal to y squared. I didn't mention this before, but remember, this is another scenario where we need y equal to the square root of x because we know that we're in terms of x. Why are we in terms of x? Because the slices are perpendicular, as you can see right here, perpendicular to the x-axis. All right, so here we go. We have a rectangle. Step number 1, what's the area of a rectangle? Well, the area of a rectangle is base times height. Well, they're telling us that the height is 2 all the time, so I can go ahead and substitute that in place of h. So the area of these rectangles will be 2 times the base. Well, the implication there is then I need to know what is the length of the base in terms of this function. Well, again, the distance from here to here is going to be governed by the curve, and so that curve is the square root of x. So we know the distance from here to here is the square root of x. The distance on the other side would be the same, so that's also the square root of x. So the total distance of that base is 2 square root of x. All right, so we have our geometry work done. We know that we're going to accumulate area from 0 to 9. There's no pi. We're not revolving. So we're going to use this formula right here, which is 2 times the base dx. We know that the base is 2 square root x. Not squaring. Notice there's no square up here because that's not part of the formula for the area of a rectangle. Now, if I were going to integrate this problem, I would multiply the 2 times 2 and get 4, and I would pull it out front and get it out of my way. I would have x to the 1/2 dx, which again is a simple problem to find the integration or antiderivative of and do the arithmetic, which I'll leave to you. Example number 4 is the same thing, except for it's a quarter circle, and then we have an equilateral triangle. Now let's set up one that we have to draw ourselves. And I'm actually probably going to end up doing one of your homework problems. So let's just get this. Let's see what I'm assigning here. 1A, 1B. All right, I'll do 1C because I'm going to assign you 1A and B. So for the next example, I'm going to show you, when you do your homework, how you do this from beginning to end. Here we go. Find the volume of the solid whose base is bounded by x squared plus y squared equal to 1. Hopefully you realize that that's a circle. So your first job is to draw the circle with a radius of 1. There's 1, 1, 1, 1. There's my circle. That's my base. That is my plate. That's what my cake is going to sit on. All right, let's keep reading. The cross section is perpendicular to the x-axis. So I know that I will be in terms of x for problem number 1. It also says that we're going to slice the cake into semicircles. Now, I am not going to try to draw this three-dimensionally, but what I am going to draw is the base of the semicircle. In other words, I'm going to put in a representative slice. Okay? Now, that would be the base of my semicircle. Now, if you're looking at it from the x-axis view, okay, so I'm drawing this as if we're flying in an airplane and we're looking down. Basically, we wouldn't see the semicircle. We would just see the line. But if I were walking towards, here's me walking towards, and I was looking at that object, what I would see is a semicircle. What I've just drawn on my figure is the base of one semicircle, okay? And that's really the part that I need to know. All right, so here we go. Geometry. Area of a semicircle is pi r squared over 2. So what do I need to know? I need to know what is the length of the radius. Be careful. It is a semicircle. So the radius is going to be the distance from here to here. If I go all the way across, I'll have a diameter. Now, since this equation is x squared plus y squared equal to 1, I'm supposed to be in terms of x, so I need to solve this equation for y. If I solve the equation for y, I'll get y equal to the square root of 1 minus x squared. Now, technically, yes, for those of you who want to ask the question, it's plus and minus, but the distance from here to here is only from the x-axis to the positive side of the circle. So this distance that I just highlighted is the positive square root of 1 minus x squared. That is the length of my radius. Now again, I don't want to go all the way across because I'm trying to find the radius of the semicircle. So if you come back over here to this figure, I only want the radius. That's what I'm trying to figure out. So the radius is the square root of 1 minus x squared. Here we go. Let's set up our integral. Now you can see that we're going to start our collection. Let's see. We're going to start our collection of area at -1, and we're going to stop at +1. Now, because this is a circle, just so you know, you could have started at 0, go to +1, and then double your answer, either way. But I'm going to say that we're going to start at -1 to +1. Now, what are we collecting the area of? Well, we're collecting the area of a lot of semicircles. And so here's my formula for the area of a semicircle. Now the pi over 2, since it's a constant or coefficient, I'm going to get it out front. And then all I need is my r squared. Well, here's r, and I have to square it. So I have square root of 1 minus x squared squared dx. From there you can do the problem because you can see that the square is going to take off the square root. All right, let's do one more problem. And then I'll leave. You can work on the rest of them yourself and bring in your questions. Number 2 is another problem that is the cross sections are perpendicular to the x-axis, so we are in terms of x. And this time we have a solid whose base is bounded by the x-axis, the y-axis, and the line y equal to -x plus 4. So let's see what the plate or the base looks like. All right, -x plus 4, 1, 2, 3, 4. Down 1, right 1. Down 1, right 1. And so we have a line, okay, that looks like that. And it says we're bounded by the x-axis and the y-axis. So this is kind of like a little triangular sort of plate. Let me pick one that I'm not assigning to you. Let's do 2B. Let's do 2... Yeah, let's do 2B. All right, this time we're putting in squares. So I'm going to put in a representative slice. Okay, again, that would be what it looks like if you're flying over in an airplane. But if I were looking at it from the x-axis, again, if I were walking towards the object and I was looking at it, what I would see is this, a square. What I'm trying to figure out is how long is that side. So this distance right here is this right here, and I'm trying to figure out how long is that side. Geometry time. The formula for the area of a square, side squared. So what do I need? I need the length of a side in terms of this given function. Well, I think you can see that the distance from the x-axis to the line is clearly going to be negative x plus 4. So my side is equal to negative x plus 4. All right, now we're ready to collect our area. We're going to accumulate all that area. We're going to start at an x value of 0 right there. We're going to stop at an x value right here. So we need to figure out where that line is crossing the x-axis. If you set that equal to 0 and solve, you'll get 4. So we're going from 0 to 4. What's the geometry formula? S squared. S is negative x plus 4. So we have negative x plus 4 squared dx. And from there, you know how to take it. All right, hopefully this is enough to get you started and to be able to think about how to do these problems. What I would like for you to do on this page and probably the next page are 1A. This should be done on notebook paper. 1B, 2A, 2C, 3B, 4, 6, 8. The answers to these problems are in the packet. They're not guaranteed, so if you think that I made a mistake, you're welcome to let me know that. But hopefully this will get you a good start if you are not here for the lesson.